Welcome to this lecture on Generalizing BFSS10, Matrix Yang-Mills Quantum Mechanics. We begin from the original BFSS10 model, the one-dimensional reduction of 10-dimensional n equals 1 super Yang-Mills theory, describing ND0 branes and realizing the maximally supersymmetric quantum mechanics with 16 supercharges. Our goal is to generalize this framework in two complementary ways. First, by lowering the number of bosonic matrices from 9 to D, obtaining a family of lower-dimensional BFSS sub D+1 models selected by Fierz closure, specifically for D equal 2, 3, 5, and 9. And second, by adding maximally supersymmetric mass deformations known as BMN-type models, which preserve all supercharges while curving the background into a PP wave geometry. We will see how these models connect gauge theory and gravity through the DLCQ of M theory, with dual descriptions involving black zero branes, PP waves, and bubbling geometries. Finally, we'll explore two key examples: BMN10, the mass-deformed M-theory matrix model with fuzzy sphere vacua and LLM bubbling geometries, and BMN3, a lower-dimensional analog describing non-critical supermembranes in 4-dimensional M-theory and D0 branes in 3-dimensional string theory. In BMN3, the circular motion solution plays the role of the fuzzy sphere vacuum of BMN10. In this lower dimension, the analogous black zero brane and PP wave geometries are postulated to serve as the dual gravity backgrounds, mirroring the higher dimensional correspondence. The BFSS10 model comes from reducing 10-dimensional super Yang-Mills to one-time dimension. It describes ND0 branes with 16 supercharges. To generalize it, we replace the SO9 Clifford algebra by SOD, truncate the matrices to D fields, and demand the same supersymmetric closure. Bakke, Reinecke, and Rittenberg showed that this closure works only in special dimensions allowed by the real Fierz identities. In each dimension D, the irreducible representation of the real Clifford algebra CL of D defines spinors of size 2 to the floor of D over 2. Even dimensions give 2 to the D over 2 components. Odd ones give 2 to the D minus 1 over 2. Because of Bott periodicity, Clifford algebras with the same D mod 8 have equivalent Spinor representations, so both the Spinor types and the Fierz identities repeat modulo 8, determining when supersymmetry can close. In this model, the bosons X sub A are Hermitian n by n matrices, coordinates of D branes, and P sub A are their conjugate momenta. The fermions lambda sub alpha form a real Clifford algebra, generated by the gamma matrices gamma superscript A, which is given in equations 4, 5, and 6. The supercharge combines P sub A and commutators of X sub B and X sub C through these gamma matrices, as in the ansatz given in equation 7, while the Gauss constraint L sub A, built from the U of n structure constants F sub A, B, C, enforces gauge invariance and ensures supersymmetry closure. Both the ansatz, equation 7, and the form of the gauge symmetry generators, equation 8, will be verified as follows. We start by computing the anti-commutator of the supercharges, curly bracket Q sub alpha comma Q sub beta, which produces three types of terms. First, a delta sub alpha beta times the Hamiltonian tilde H. Second, a gamma superscript A sub alpha beta times X sub A superscript A times the Gauss constraint tilde L sub A. And third, a residual term involving the tensor F sub alpha beta semicolon alpha prime beta prime superscript A. The goal is to obtain a minimal supersymmetry algebra in 0 plus 1 dimensions, where the closure reads curly bracket Q sub alpha comma Q sub beta equals 2 delta sub alpha beta H plus 2g gamma superscript A sub alpha beta X sub A superscript A L sub A. The Gauss constraints commute with both the Hamiltonian and the supercharges, and the Hamiltonian commutes with the supercharges up to the Gauss constraints. To achieve this closure in this structure, the Fierz identity should project out all higher-rank Clifford elements, which may break gauge invariance, enforcing thus the condition that only the scalar and vector channels remain. Explicitly, F sub alpha beta semicolon alpha prime beta prime superscript A must equal delta sub alpha beta gamma superscript A sub alpha prime beta prime minus delta sub alpha prime beta prime gamma superscript A sub alpha beta. Equation 15 is our fundamental Fierz identity. This projection yields the correct Hamiltonian, the Gauss constraint, and finally fixes the number of real supercharges to m sub Fierz equals 2 times d minus 1. We now need to compare two counts. First, this obtained m sub Fierz, which is equal 2 times d minus 1. Second, the original m sub Cliff, which is equal 2 to the power floor of d over 2. Requiring equality gives only few possible dimensions where the Fierz identity, given by equation 15, actually holds. These are d equal 2, 3, 5, and 9. The solutions are BFSS3 with d equals 2 and m equals 2, BFSS4 with d equals 3 and m equals 4, BFSS6 with d equals 5 and m equals 8, and BFSS10 with d equals 9 and m equals 16. But why not BFSS2? For d equals 1, m sub Fierz is 0, but m sub Cliff is 1, so the matching fails, even though the dynamics need not be trivial. Beyond dimensional reduction, we can add mass while preserving all supersymmetries. These mass-deformed BFSS models are also called the BMN models. The Hamiltonian is h superscript mu equals h sub BFSS plus mass deformation terms, as shown in equation 19. This Hamiltonian typically involves three parts: a quadratic matrix mass term, a cubic Chern-Simons or Myers term, and a matching fermion mass term to complete supersymmetry. With mu not equal to 0, the anticommutator, curly bracket q superscript mu sub alpha, q superscript mu sub beta, shown in equation 20, includes rotation generators r superscript ab through c sub ab gamma superscript ab. The supercharge then precesses, as shown in equation 21, bracket h superscript mu, q superscript mu equals I mu times script m dot gamma acting on q. In equations 19, 20, and 21, c sub ab, the object script m, capital pi, and t superscript abc are all fixed by the requirements of supersymmetry and the Fierz identity. Indeed, Fierz identities fix which mass terms and coefficients are allowed, yielding the BMN family for d equals 9, 5, 3, 2, and 1, preserving 16, 8, 4, 2, and 1 plus 1 supercharges, respectively. In summary, we have two generalizations of BFSS10, lower d descendants via SO9 to SO of d, and maximally supersymmetric mass deformations for each admissible d. Gauge gravity in this context starts from the allowed spacetime dimensions. Superstring theory and super-Yang-Mills exist only for d sub ym equals d plus 1 in the set 10, 6, 4, 3, 2, with real supersymmetry script n equal to 16, 8, 4, 2, 1 plus 1. By dimensional reduction to one-time dimension, we obtain BFSS sub d plus 1, preserving all supercharges. This includes the supersymmetry-enhanced BFSS2. On the gravity side, each BFSS sub d plus 1 describes the low-energy dynamics of ND0 branes in light cone gauge. The dual background is superstring theory in d sub ym dimensions around a black zero brane. Equivalently, these models quantize supermembranes and superparticles in d equals d sub ym plus 1 equals d plus 2. Supermembranes exist only in d equals 3, 4, 5, 7, and 11, where supergravity is the low-energy limit of M theory in those dimensions. In each BFSS sub d plus 1, a maximally supersymmetric mass deformation, BMN sub d plus 1, introduces a pp wave scale mu while preserving all supercharges. The dynamics are those of superparticles moving in maximally supersymmetric pp wave backgrounds of d-dimensional M theory. The dual gravity is given by half BPS bubbling geometries, LLM droplet solutions that encode the BMN vacua. BMN10 is the unique one-parameter deformation of BFSS that preserves all 16 supercharges. The deformation introduces a mass scale mu and Myers-type cubic interactions encoding a four-form flux F, placing M theory in the maximally supersymmetric pp wave background. The metric is given in equation 24, and the four-form flux F plus 789 equals mu. The action is S sub BMN equals S sub BFSS plus a mass term, quadratic masses for X, a cubic Chern-Simons or Myers term, and a fermion mass term. Supersymmetry variations generate SU24 algebra, and the maximally supersymmetric static vacuum is a fuzzy sphere. Commutator of xi and xj equals I alpha epsilon j kxk with alpha equals mu over 3, spanning the 7, 8, 9 directions. BMN has a richer vacuum structure, not a single flat vacuum, but many fuzzy sphere vacua, giant gravitons. The dual 11-dimensional background is not just the homogeneous PP wave, but a family of half BPS bubbling geometries asymptotic to it. Each BMN fuzzy sphere maps to a specific LM bubbling geometry, due to Lin, Lunin, and Maldacena, 2004. BMN is the DLCQ of M-theory on the maximally supersymmetric PP wave, whose half BPS sector is LLM bubbling geometries. The dual gravity is the 10-dimensional type 2 APP wave with LLM generalizations, uplifting to the 11-dimensional PP wave. These LLM geometries are encoded by a single harmonic function on a 2-dimensional droplet plane. Each droplet corresponds to giant gravitons, and the BMN fuzzy sphere vacua reproduce the quantized droplet data. BFSS3 and its mass-deformed version BMN3 are obtained by dimensionally reducing 3-dimensional super-Yang-Mills to 1 dimension, then adding a deformation that preserves all supersymmetries. These models provide lower-dimensional approximations to BFSS10 and BMN10, describing non-critical supermembranes in 4 dimensions and D0 brane dynamics in 3-dimensional string theory with a corresponding gravity dual. The field content includes 2 Hermitian matrices, X1 and X2, a gauge field A sub T, and a 2-component Majorana Spinor psi in the adjoint of SU of n. The action, given in equation 30, contains the kinetic terms, the commutator potential, and the deformation terms proportional to minus mu squared x sub a squared and I mu psi bar psi, representing the mass deformation. Both bosons and fermions transform adjointly under SU of n gauge symmetry. The supersymmetry algebra follows the Clifford 2 real structure, with the anticommutator of Q and Q bar proportional to H minus mu over 6m12, and a BPS bound saturated by circular configurations. In sum, BFSS3 and BMN3 are lower-dimensional truncations of the 10-dimensional models, preserving the same gauge gravity correspondence structure, where the circular solution is the analog of the fuzzy sphere vacuum in BMN10. The BFSS10 model is the 0 plus 1-dimensional reduction of 10-dimensional n equals 1 super-Yang-Mills with 16 supercharges, describing a system of ND0 branes. We generalize it in 2 ways. First, by reducing the number of bosonic matrices from 9 to D, and second, by adding maximally supersymmetric mass deformations of the BMN type. Fierz closure determines the allowed dimensions through the relation m sub Fierz equals 2 times D minus 1, matching with the Clifford Spinor size 2 to the floor of D over 2. This selects D equal 2, 3, 5, and 9, corresponding to the BFSS 3, 4, 6, and 10 models, with 2, 4, 8, and 16 real supercharges. Each BFSS sub D plus 1 represents the discrete light cone quantization of D0 branes, dual to superstring theory on black zero brane backgrounds. Their BMN deformations introduce PP wave geometries preserving maximal supersymmetry, uplifting to M-theory in D equals D plus 2, with half BPS sectors described by LLM-type bubbling geometries, where BMN vacua correspond to LLM droplets.